NCR Corporation is a leader in omnichannel solutions, turning everyday interactions with businesses into exceptional experiences. With its software, hardware, and portfolio of services, NCR enables nearly 700 million transactions daily across financial, retail, hospitality, travel, telecom, and technology industries. NCR solutions run the everyday transactions that make your life easier. NCR is headquartered in Atlanta, Georgia, with about 30,000 employees and does business in 180 countries.
So, hi, thanks for all for coming. My name is Hubicki. I am a professor of mechanical engineering at the FAMU FSU College of Engineering. It's a joint College of Engineering between Florida State University and Florida A&M University down in Tallahassee. So what I do is I teach students, college students, about robotics, and also I run a research lab called the Optimal Robotics Laboratory, where I get to work with bipedal robots. There's a little video of our current bipedal robot. It's called Cassie, okay? Cassie is built by a company called Agility Robotics, which is actually a company founded by my friends when I was doing my PhD at Oregon State. We had spent 5 years making the predecessor to this robot as part of my PhD. And after I graduated, I went and did something called a postdoc, where you go and work in a different laboratory, and they started a company where they built these Cassie robots. So that way, researchers like me can get one and then start programming it right away. And so I just started my job here down in Tallahassee, and our Cassie is called the Tallahassee Cassie. Okay? Yeah, thank you. Glad you like it. Anyway, but Cassie is a bipedal robot. It's about 70 pounds. It can walk around. Here it can stomp up this curb here. Cassie is actually blind, by the way. Cassie can't see. What we do is we have a little drone controller. We tell it forward, backward, left, right, that kind of thing, and it just goes. It doesn't need to see what's in front of it in order to walk around. So that's what we're doing with Tallahassee Cassie now. But what I'm going to talk to you today are about the general challenges of getting robots to walk around on 2 legs, okay? And some of the previous work that went into developing this kind of technology. But you might be saying, Christian, why legs? Well, they're cool, for one, all right? That's my first answer, all right? It's always my first answer. But you might be thinking, well, really, why not wheels? Wheels are great. They get around and, on roads without a problem under normal circumstances. But sometimes things go a little crazy. You might be happy that you have legs. And now he's fine. Look at that. So look at that. It's very amazing. Spider-Man was on that motorcycle, okay? But more generally, robots, for the most part, up to this point, have mostly been in factories, places that are very, very well controlled. There's not a lot of people getting in its way. It can just pick up a part and then put it down in another place, just do that all over and over again. It's all very well controlled. But for the robots to go in the future, they have to come and play basically in our sandbox. They have to play by our rules. They have to get up and down stairs. They have to be able to get around in our homes and in our places of work as well as we can. Okay? And also that's useful because we want robots to sometimes go into places that are dangerous. The places where we could go but are perhaps too dangerous right now, such as a burning building, for instance, or there's actually a malfunctioning nuclear power plant. Not my favorite place to hang out. All right. We want to go to dangerous places. But more importantly for me is that we have 2 legs, okay? And sometimes we have a hard time walking. But there's all this potential for robotic devices like exoskeletons or prosthetics to help people walk again that have motors, okay? And if we want to know algorithms that make people walk again, it's actually really handy to learn to figure it out through robots first. So I learn a little bit about how people walk every time we make a robot walk a little better. So here's an example of a bipedal robot, okay? This was something called the DARPA Robotics Challenge back in 2015, where there was this simulated nuclear disaster where you see a valve on the wall where we wanted this robot to be able to go and shut off the relief valve, shut it off, okay? This was IHMC Robotics. I was not involved with this team. They were an amazing team of researchers and one of many teams that competed in this DARPA Robotics Challenge. And you can watch this robot it has to get around, get on top of this rubble pile, and see how it's sort of navigating. And it's really amazing. They do all kinds of crazy, interesting computations where they look through their laser with a little LiDAR detector. They see what's on the ground in front of it, plan out its motion, and then they put their feet down and they move through it. Very, very interesting work. But it's also an excellent example of how robotic approaches to walking generally work. You'll notice what it's doing is it will put its foot down, transfer its center of mass over its foot, pick up its foot, stay balanced, put down the other, and then transfer its weight, very methodically. The idea is that if I'm never tipping, then I'm never falling, and I'm stable. That's one way to make sure your robot doesn't fall over. But we don't really walk that way. As people, we kind of stick our foot out, fall, and catch ourselves. And this is actually a much more efficient way to walk. We don't have to spend much energy that way. If you try to walk like this, one, you'll look a little silly, but also it's very tiring very quickly, okay? So one of the lessons that we're learning is to be more efficient with our robots. And so how do we go about doing this? Some of it is in the robot design, and a lot of it's also in our approach to walking, all right? So that was the idea behind this robot right here, okay? You might say this is a very grainy old video, and that doesn't look much like a robot. You would be correct. So what this device here is, it's just basically an erector set. Do people still know what erector sets are? Okay, someone, okay, all right. They're basically pieces of metal that are sort of connected to each other, right? There's no motors, there's no computers, no batteries, no nothing on this robot. It's just a piece of mechanics, okay? And this researcher here, Tad McGeer, what he's gonna do is gonna take this little thing with legs and he's gonna push it down a very gentle slope, okay? It's basically gonna so it's basically on a little hill. He's gonna give it a push. And it walks. Isn't that interesting? Yeah. And look how natural it kind of looks, too. By doing almost nothing at all. It's got no motors on it whatsoever. So that's pretty neat in my book. And so that's a lesson that we learn, that if we sort of stick our feet out and try to catch ourselves over and over again, you can walk with almost no energy consumption at all. Okay? And that's a big problem for robots, is energy consumption. So that was the idea behind this robot here that I worked on called Atreus. Okay? It was a big collaborative project to make a robot that still walks, but in a much more efficient way. Okay? So the thing about Atreus is it is 260 pounds. It's a pretty big robot. Okay? It's about yay tall. All right? And we wanted to set out to make this robot walk more efficiently, where it sort of sticks out its foot and catches itself. The problem with that is that when you are in this state of falling with your robot and catching yourself, the equations of motion for your robot become pretty big. In fact, if you printed it out on like size 8-point font on pieces of paper, the equations, they would easily cover a football field. Okay? So one of the big challenges with this robot was coming up with an algorithm that could solve these equations over and over and over and over again and teach this robot how to walk. And that was a big challenge. So when we solve that algorithm, it tells all the robot's joints how to move, all 13 of its motors, okay? And then when you do that, you put it on the robot, and it starts to walk on this treadmill here, okay? So you can see me in the corner there. I look very excited because I think we got this result at 6 in the morning. That's why I look so jovial in that photo. But yeah, so if you can see the robot sort of sticking its foot out and catching itself with every step. It's sort of like it's got this sort of natural looking way of making the robot, of rolling from your heel to your toe over and over again. And we didn't tell the robot to do that. All we did was we tell the algorithm, come up with the most energy efficient way to walk. And that's what it did. It walked like a person. And we thought that that was a really interesting result. So, and as a result, this robot was the most efficient humanoid robot at its time. As a result of this very, very simple natural motion. So we're very proud of that. So you also might be thinking, where does one find those sweet robot shoes? Well, I will tell you. Okay, you go to the shoe store. All right, just an ordinary. So we took the robot foot, we unbolted it, and we took it to Journeys. okay? And this very helpful gentleman sized the robot foot on the scale, a little scale right there. You know, he found it, it's a size 14, by the way, men's. All right. He was a complete professional. I was actually a little insulted. He wasn't more impressed we came up with a robot foot, but that's okay. He was doing his job very well. So that's where you get those robot shoes. So, but another lesson we learned about robots is to learn from nature more explicitly. There are lots of creatures that run around on two legs. All right. The humans aren't just one of them. There's also birds. Okay. This is a bird species called the helmeted guinea fowl, or Numida meleagris, okay, that we did some experiments with as part of a collaboration with a veterinary college in London. But you might be saying, Christian, why birds? Because they're cool, okay? They are. They're really good. So why would we look at birds? They're also really good runners, okay? This is one of those helmeted guinea fowl. It's about to run over what it thinks is solid ground, but is in fact just tissue paper. Oh yeah, I know. Oh no, indeed, and no, indeed. So it's a trap, okay? So how's it going to respond to this trap? Well, it runs, steps in through the tissue paper. Oh, keeps going. That's pretty good. I can't do that, but that bird can, okay? So we learned a lot about the stability, how to make robots more stable by looking at creatures like birds. Also, birds come in all shapes and sizes. Birds that run around that are even not normally naturally flyers. Okay, ostriches are huge, and tiny bobwhite quail are very tiny. And the range between those birds in terms of size and weight is about 500 times. Okay, it's hard to get humans that span that range in mass, okay? What that gives us is a broad sample of creatures to look at. So we want robots, all different sizes to walk. They're a great example. So I had the pleasure of working with Dr. Monica Daly at the Royal Veterinary College, and we set up this experiment, and she's excellent at this, and where we have this runway, okay? And then we're going to take a bird, this bird named Greg, in the corner over there, all right? And we're going to encourage Greg to run across this runway, okay? And go, there he goes, this is slip sliding away, okay? All right? So Greg runs, all right. Greg runs really well. We love Greg. So, but one thing that you might not have noticed is that in the floor, we had force sensors. Like imagine a bathroom scale that gives you data every millisecond, okay? So pretty awesome bathroom scale. And we put it through a motion capture field. To see how it would run so fast and the way it moved its legs. By the way, if you're ever curious, if you want to ever put motion capture markers on a chicken, use hair extension glue. You learned it here first. So more than that, also we put birds over obstacles. This is a turkey that we had just run over this obstacle, over this same sort of runway setup. And we did this for a whole bunch of different species, okay? And in fact, here are these 5 species that span that 500-fold mass range we talked about. And one thing we learned is in spite of this huge range, that they run almost exactly the same in such a similar way. And we were stunned by this because they're not only just big to small, they also have different sort of bone structures to how their bones are set up, and they all ran the same way. And we learned a lot about how to put down the legs of a robot from these birds, which I thought was really interesting. So my final lesson here was sort of be flexible and go with the flow. This is something we learned in terms of making these robots go nicely. So what do I mean? Okay, so here's a robot. It's a robot arm, and there's a very brave gentleman who has strapped himself to this robot arm. Okay, don't do this. Don't do this, he's fine. All right, so the lesson here is the reason that this very brave gentleman is so confident is that there's a motor at every joint of this robot that has a lot of power behind it that can very tightly restrict its control to make sure it goes exactly where you want. You know, it's very rigid, it doesn't flop around, so that's how it can be so precise with having this gentleman float around like that. Wouldn't recommend it though. So, which takes me to my next example of something that isn't anything like this, okay? It's not even a robot, it's a fish, okay? This is a rainbow trout. All right, and it's swimming in this little experiment behind a rock. And then you'll see it starts swimming upstream like that, okay? You catch that? How it swam upstream? You might say, Christian, that's not very interesting. Fish swim upstream all the time. But this is a dead fish. Yeah, yeah. So how does a dead fish swim upstream? Well, it's flexible, and what's happening is the water around it is pushing the flexible body of that rainbow trout in such a way that it's actually being propelled upstream. That's fascinating, right? So we kind of learned that if you have a body layout that is designed just right, that's flexible, and if it's flexible in the right ways, then it doesn't need a lot of control to get something done. So very interesting, I think. So they did a good job in that research. So, which led us to our next robot, which is called Atreus. All right, this is the predecessor to Cassie I was talking about. And this was like a big 5-year-long project with like 40 researchers over the years working on this thing to build this robot. It's all the way on the right over there is the final iteration. But the idea was we wanted something very simple and flexible as a robot body plan, like this simple little mass on a spring, okay? So we built this robot to just be as close as we could to this very simple, flexible mass on a spring, kind of like a pogo stick. So that's why we named the robot Atreus. It stands for assume the robot is a sphere. That's what the acronym is for. There's a physics joke behind that. I can tell you after the talk in terms of what that relates to. So the thing about Atreus is that by being flexible, it actually allowed us to be a lot more agile in how we get around with this robot. So let's show some videos. So this is Atreus getting around here. On the GoPro cam here. We took it down to the DARPA Robotics Challenge I showed earlier. That's a big demonstration. We have that big gantry overhead to catch it in case it falls so I don't cry because my PhD thesis is broken. You know. But we had it walking around and running. It was a very interesting proof of concept. This robot is 140 pounds, has only 6 motors on it. Okay? There are probably more motors in many of your household appliances that are on Atreus. And yet it can step over all these obstacles. We actually got it up to a pretty fast speed. We got it to like a nice light jog, about 9 kilometers an hour, which was cool. But how do we do this, okay? Well, we first started with making controllers that were very simple, where we just had march in place, okay? And then we would test its stability. Now, how we tested stability? In a very simple way. Yeah, so we just, we added some perturbations into the mix, as we said. Eventually, we took down the robot. We knocked it down. You might be wondering how that happened. Well, there's an emergency stop button on the robot. So I point that. But we tuned up the stability by doing these experiments, right? Okay, my friend Mikhail, he's a good shot with the dodgeball. It's very good. So, and we also tried to tune it on different kinds of terrain, all right? This is an obstacle that it doesn't see. Okay, we just told the robot, go forward. And it's like, okay, I trust you. And its job is just to keep trucking on and recover from any disturbances it gets. And this is my favorite run right here, okay? It appears to trip a little bit. But I'll slow it down for you, okay, as to what happened here. So it catches the toe right on the edge. And it catches itself. Pretty good, right? We were very proud of that result. So it just treats the ground as just some disturbance to recover from. It doesn't need to see it coming. It doesn't need to plan every step ahead of it. It can just go. And you can do that. You can walk around in some kind of obstacle-laden environment with your being blindfolded and still walk around and stumble and not fall over, right? You know, we have that ability, as does Atreus, okay? And the last thing we did with Atreus here is we took it out to the research stadium at Oregon State University, and we just told it to go faster, 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 up to the highest speed we can get with these motors, okay? And we had it, accelerate and come down to a stop right here. But when we looked at the force data on the robot, this is the forces against the ground. When it's non-zero, when it's above zero, there's a foot on the ground. When it is zero, it's in the air. We just told it to go faster and it started running. We didn't tell it to run, but it just did. So so that is the way that we learned the lessons and how to control these robots to be more sort of agile and efficient, okay? So finally, sort of what's next here? So as I mentioned, we have Tallahassee Cassie, okay? If you check out my Instagram page, occasionally we do, this was a live stream we did. We just walked it around Florida State campus as to do our sort of like test runs, okay? But I want to get Tallahassee Cassie running around with as much agility and efficiency as other bipedal creatures, like an ostrich, okay? I want it to be able to run around turns. And I suspect that if we get Cassie running the best it can, it will, as a natural consequence, start running like an ostrich. So, also, how do I get involved? You know, some people like robots, right? Do people like robots here? Good, some? Okay, good, at least a couple. Fantastic, a lot of you guys, great. How do you get involved? Well, you don't have to, you know, you can start right now, okay? You know, when I was a little kid, I played with Legos, right? That was, I think, my first robot, okay? Legos are a great way to get involved. There are also high school robotics teams, middle school robotics teams. I did FIRST Robotics. I know that there's VEX. Oh, I saw a FIRST Robotics person. Yes, yes. What team number were you? 856? 836. I was team 7. Team 7, yeah. That'll give you a hint how old I am. So anyway, so you can start getting involved in high school. If you want to go into college, you can major in virtually any kind of engineering field. You know, mechanical, electrical, computer science, biomedical even. I actually have a civil engineer in my lab right now, and he's learning to do robotics from a civil engineering background. So don't feel limited. In terms of courses you want to take, things like math and sciences, okay, are a big one. But really, just get your hands dirty. Just start making robots. And finally, one last thing I would say about robotics. It sort of is a big general thing, all right? When I talk to astronomers, and they talk about what they like about astronomy, is that they can look at the stars in a completely different way, a new way, than they could before. I thought that was really cool. And for robotics, I actually look at my everyday life in a new way. You know, anytime I do something, like I want to toss and catch this remote, you know, you can think about, how would a robot do that? And that really kind of opens up a new perspective on sort of just your daily life tasks. And it makes life a little more interesting for me. And you know, in general, I just find robotics to be cool. So with that, thank you so much. I would love to take your questions, all right?